Hello, I'm Mehdi Gorzadeh. I'm PhD student in Software Engineering Lab at University of Mons. In this study, we have proposed a new approach for detecting bots in GitHub pull request activities based on comment similarity. This research is presented to the second international workshop on bots in software engineering. To begin, we need to get familiar with the concept of online coding platform. Today, software developers, especially open source developers, are increasingly using these platforms to commit their changes to codebase, use new methods of code contribution like pull request, and also doing code reviews. As these platforms are getting more and more popular and they host millions of projects, maintainers tend to rely on bots to carry out routine tasks and to interact with project members to facilitate their works. Studies have shown that bots improve collaborative development in several different ways. For example, improving software quality by automated refactoring, generating patches for bugs, continuous integration, automatically closing abundant issues and pull requests. What's a pull request? It's a method of code contribution which allows developers to participate in different projects without having direct commit access. To submit a pull request, one can create a fork or clone a repository, make changes, and submit a pull request easily by putting a title, a description, and clicking on the Create Pull Request button. After submitting a pull request, it will appear in the list of pull requests, and maintainers will decide whether to merge it or not according to the quality of changes. If you have a look at the list of pull requests, we can see that there are a lot of comments and discussions in these pull requests. And if we open one of these, we can see that bots are involved in these discussions. We believe this can bias studies targeted pull-based development and more generally social codings. For example, the presence of bots makes it difficult for empirical studies to distinguish human behavior from automated behavior. And other studies like identity merging or social aspects like contributor onboarding, contributor abandonment, team productivity, and team collaborations can be influenced by the presence of bots. More specifically, in our last study about acceptance or rejection of pull requests, we noticed that proportion of accepted pull requests with presence of bots is almost twice pull requests without bot comments. This means they need to be considered by researchers. This subject is directly related to our goal in SequaAssist project to study software ecosystem health. So we decided to find a solution for this problem. The current method to identify bots on GitHub is based on a combination of different methods. It's a manual and effort-prone process and not easily reproducible, like looking for previous studies about well-known bots and the presence of a string bot in user identity. So, having a ground truth was an important task in our study. We created a dataset of accounts that are currently active in 1,200 projects of cargo ecosystem. We manually identified 42 bots and 250 human accounts, and all of these accounts manually and independently checked and verified by two distinct authors of this paper. The underlying idea of our study, which is to propose an automated approach for detecting bots in GitHub, is based on the hypothesis that bots exhibit more repetitive messages than humans, since they are expected to automate repetitive tasks, while the variation in comments made by humans is expected to be higher. This figure shows comments of a sample bot in our dataset, and as it's clear, comments are very similar. So we decided to measure this similarity of comments by two well-known distance metrics. The first one, Levenshtein edit distance, which works more on the structure of the text by counting the number of single character edits like deletion, insertion, or character replacement. And the second one, Jaccard distance, which works more on the similarity of the content and compares the number of distinct common words in two strings with the total number of distinct words in them. We computed the Levenshtein and Jaccard distance of all pairs of PR messages of each identity. The figure shows mean Levenshtein and Jaccard distance of all comments of each identity. Clearly, humans have higher Jaccard and Levenshtein distance than bots. Also, we can see that both distances have very similar results, but the presence of dots outside the diagonal indicates that both distance metrics are not redundant. In this figure, we can find bots and human accounts with the same Jaccard distance but different Levenshtein distance, and conversely, we can find human and bot accounts with the same Levenshtein distance and different Jaccard distance. Even if humans can be identified on the basis of higher mean distance, this does not effectively distinguish them from bots, since we observed that some bots also have such high mean distances. We manually inspected those bots and we noticed that while they do have repetitive messages, these messages follow several distinct patterns, implying a higher distance value when messages belong to different message patterns. We assume this similarity comparison works, but it's not enough to catch all bots. Therefore, we came up with the idea of counting the number of patterns. In this figure, we can see comments of a DevOps bot with 3 different message patterns. So, we decided to compute the similarity of sets of comments instead of all comments, as we knew messages follow several distinct patterns. We guess that human comments spread across many small clusters and bots will have very small number of large clusters. Therefore, we applied an intermediate clustering to identify the number of patterns of comments for each identity. We used DBScan, one of the popular machine learning techniques for clustering tasks. We selected this technique because it has the advantage of not requiring to specify the number of expected clusters. It can generate clusters of unequal size, and also it allows clusters to contain a single item. We used combined Levenshtein and Jaccard distance as our distance metric. The figure shows the number of resulting clusters and the number of considered messages for each identity. As we can see clearly, bots have a lower number of clusters regardless of the number of messages, and all 42 bots have 10 clusters or less. We can also observe that 249 out of 250 humans have at least 14 clusters. Our approach can classify bots based on the threshold of 10 clusters with the recall of 100 and the accuracy of 97.7%. The limitation of our work mainly lies on the size of our dataset. We have a dataset of only 292 GitHub identities, all from cargo ecosystem. Another limitation of our work is that the cluster of comments is the only decision factor, while, as we saw, the number of comments could be considered as another factor. We decided to continue this study, so we already manually verified 5,000 accounts from 169,000 repositories from 37 ecosystems. We want to create a classification model instead of a threshold for clusters, and also we want to include more features like number of comments, empty comments, and Gini value as distinguishing metrics. And also we want to provide a tool. To sum up, we explained about pull-based development and presence of bots in social coding platforms and how this presence can affect studies related to software ecosystem health. We explained our approach and the result. Our approach is based on the comment similarity and clusters of comments. We computed clusters of comments with the combination of Jaccard and Levenshtein distances. We showed that our approach classifies accounts with high precision and recall. We also further worked on this subject and we created a bigger dataset and we considered more features to make a better model to classify, And also we decided to create a tool to make it more useful for the community. Thanks for listening, and any question?